All right. Let's continue our discussion of capacitors. If it looks like I've skipped over something, please refresh my memory. Because I've done something similar in the 152 class, so there are certain memories that I think I know I did it, and I might have done it for the other group. So, if I have a parallel plate capacitor, what is the formula for capacitance? Is it charge over voltage?
Yes.
All right, so that's always going to be true. Charge over the voltage, where it's a positive number ultimately. Yes, one of the plates is positive, one's negative, and the voltage could be positive or negative depending on which way you go across it, but we're only looking at positive numbers here. That's always true for capacitors, but what about for parallel plate capacitors specifically? And this relates to the lab that you did 2 days ago. Benjamin, it looked like you were about to give the answer.
I'm blanking on what the little E.
Epsilon?
The epsilon, yes.
Okay.
Kappa epsilon area over distance.
Kappa epsilon sub 0.
Yes.
A over D. All right. Now, if I so I have this hooked up to a battery. The plate's charged. I know the ratio of charge to voltage is a constant because the capacitance is dependent upon the configuration, the geometry of it. It's and constants. I'm going to reconfigure this instead, where I've got the wire splitting. Does the capacitance change?
No.
Why not?
Well, none of those constants have changed.
Yeah. I mean, all it is just changing the mechanism which the charges get onto the plates or off the plates. But the geometry stays the same, so the capacitance is the same. All right, so now what I'm going to do is I'm going to take this and I got it split, so charges will go one way or the other. I'm going to put a little break in this so that the total area of the dual plate, so the total area of those is the same as it was before. Has the total capacitance changed?
Yes.
How?
You said you put the plates closer?
Well, I'm not putting the plates closer. All I've done is just take, instead of having the plate like this, I just separated them so that I now have two half the original size plates on each side.
None of the constants have changed still, because it's still the same area, it's just there's a break.
Yeah. All right. So this, assuming that the area of this whole plate and the area of these two plates are the same, the distance is the same, we have the same capacitance. Now, if I treat this as two capacitors now, my area's been cut in half, so this would be half the original capacitance, so if that's C sub 0, if I did split those in half, that would be half of C sub 0 and half of C sub 0. Or we could have split it up so that it's 1/4 and 3/4, but the total capacitance hasn't changed. So this concept here of if I have current that will split, and it can go one of two paths, go this way or well, actually, if we're talking current can go this way or it can go that way. We have a structure that is known as parallel capacitors. And the total capacitance that is stored in the parallel capacitors, well, the total capacitance, or equivalent capacitance is probably better wording, is just C1 plus C2 plus however many capacitors I have in parallel. I believe we did not do this last week. Okay.
We ended up with that formula.
Okay. So just taking a simple setup here. If I have a 3 farad capacitor here and a 4 farad capacitor there, I'm running short of 3 and 4 farad capacitors, so I pull those out and I need to put another capacitor of equal capacitance in there. What would be the equivalent capacitance? What is the equivalent capacitance? Somebody knows it.
7.
Yes. Farads. They are in parallel because if you look on each side, I have a junction here and they have the same junction. So they are on each side, they share the same junctions, plural. Therefore, they are in parallel. If I had a structure like this, this is not in parallel with those. Sorry, this is in parallel with the whole thing. It's not in parallel with either of these individually. Because this has a junction, say here and here. This has a junction here and here. And this has a junction there and there. So this does not share 2 junctions with another capacitor. We can also look at this differently. I know that the total charge being stored on this is the same total charge that is stored on that. Is that the direction I want to go? That is not the direction I want to go. I know that the voltage, that's the way I wanted to go. I know that my voltage drop across that way is the same as it is across there or across there. Kirchhoff's loop rule, I gain potential here, I have to lose potential. Either path I go, I have to lose the same amount of potential. So delta V is equal to delta V1 plus, or not plus, delta V1, which is delta, same as delta V2. I know that the total charge stored is going to be the same. In other words, that the charge on 1 plus the charge on 2 is going to be the total charge. Given this formula right here, Q is equal to C delta V. So this is C1 delta V 1, but it's the same as all the others. Plus C2 delta V is equal to C equivalent delta V. Delta V's cancel out, and you're left with this. Questions there? And let's do series. So if instead I have a capacitor here, And I want to figure out the equivalent capacitance now. Well, as soon as I hook up the battery, I have an electron that will be cruising around counterclockwise, and I'll get an electron here. That's going to push an electron off of the left-hand plate here. That electron's going to go here, which will push an electron off. So whatever charge buildup I have on this plate, I'll have some negative charge on this plate, I'll have the positive equivalent on this plate, the negative, same negative on this plate, same positive on this plate. So if this is negative Q, that's Q. That would be negative Q, that's Q. Well, I gain some potential going across the battery this way. So I gain going this way. We can go for stunning effects. Ooh. That is not what I wanted. All right. So my potential, I gain some potential going across there. I'm going to lose some going across this capacitor. I'll lose more going across that capacitor, and I'll end up back at 0. Because for any loop, if I end up back where I started, the total potential gains and losses is 0. So I gain some potential going across the battery, minus the potential going across capacitor 1, minus the potential going across capacitor 2 is equal to 0. From our generic formula over here, I know that the potential drop across the capacitor is just going to be the charge on that capacitor divided by the capacitance. So this will be Q over my equivalent capacitance. May as well bring this over to the other side, equals plus Q2 over C2. All my charges are going to be the same as outlined earlier. So those can cancel out, and what I'm left with is 1 over my equivalent capacitance. This is 1 over C1 plus 1 over C2 plus however many I have in parallel in series. So if I've got if that's a 3 farad and a 4 farad capacitor, what is my equivalent capacitance?
Wouldn't it still be the same? 7?
It is, no, definitely not. Well, you can do the formula. 1 over C equivalent is 1 over 3 plus 1 over 4.
7 over 12?
Say it again?
7 over 12?
That's not the equivalent capacitance, that is the sum of the fractions. What is the equivalent capacitance?
12 over 7?
Yep. So there's my equivalent capacitance. The two most common mistakes people make is getting them backwards. Adding series like parallel, parallel like series, and when adding the reciprocals, forgetting to take the reciprocal at the very end. So if we then took this one step further, who said some of this before? Who's had some electricity in previous physics classes? Okay. If you recall, resistors are the opposite. Okay. You're looking at me like you don't really remember that. Okay. When we get to resistors will be the opposite. We could also look at this one other way. Well, probably more than one. But if I have a plate here with some distance D1, or I have parallel plate capacitor, and then I got one over here with a distance D2. This is the equivalent of having a capacitor with the distance between the plates of D1 plus D2. that in essence, this whole part right here could disappear and we just shrink the distance, pull them closer so the total distance stays the same. And for a parallel plate capacitor, we would have kappa, just to save time, I'm just gonna write epsilon, non-epsilon sub 0. A over D1 plus D2 is equal to epsilon A over D1 plus epsilon A over D2. So this becomes 1 over D1 plus D2. Actually, I'm going about that, pass backwards. I know my equivalent capacitance is going to be epsilon A over D1 plus D2. Therefore, D1 plus D2 is equal to epsilon A over C sub naught. And that should be the same as D1. D1 would be epsilon A over C1. So this becomes epsilon A over C1 plus epsilon A over C2. And you get the same place. All right, that was not what I originally came over here to do. What I originally came over here to do was to give you a problem like this. No, we'll do this one first. We'll make it 1 farad, 2 farad, 3 farad, 4 farad, and 5 farad. What is the equivalent capacitance? Now, wherever you put the probes would make a difference. When you have the two lines extended like this, it's assumed that that's where the probes would go. If you're measuring the capacitance, you would put it like that. All right. We have all the tools. Let's do it. Which ones would we combine first?
1, 2, and 3.
We would not combine 1, 2, and 3 at the same time. We'd have to do some of that first and then something else. Because 3 is not in series with another one, it's not in parallel with another one.
So just 1 and 2.
Yeah, we do 1 and 2 first. So 1 over 1 plus 1 over 2 equals 1 over, I'll just call it C12. So C12 is equal to 2/3. So I've now reduced this to 2/3. 3. 4. 5. Now what?
We can add 2/3 and 3 together.
Okay, they are in parallel, so we've now reduced it to this top path. I've got 3 2/3, which is 11/3. Just got that. Now what?
Is the 4 not allowing us to add 11/3 and 5 together?
Correct. Or the 5's allowing you not to add 4 to the 11/3.
So do we treat them as just serial?
Yeah, series.
So it would be 9/20.
Could be what?
9/20.
29ths. So now it's reduced to 11/3, 29ths. And now you would just add them. So 53/9. Fair, I suppose. If you think about current flow, think about it like if this were water. As water flows in, the water's gonna flow in, it's gonna split again. Some's gonna go across here, some's gonna go across there. These will join up again. This current will flow through there, it'll join up again. Anywhere where the same water would flow across two capacitors, that is series. So because these are along the same path here, those are in series, those are in series. And officially, parallel would be two capacitors that have the same potential drop. That's probably not as good a definition. Same potential drop across them is a requirement, but it's not sufficient for all of them. All right. Questions?
Why aren't there the parallel lines on 29s? Or whatever.
Oh, the 29, oh, because I got sloppy.
Okay, I was just wondering if there was anything.
They should be there.
Okay.
So doing all that series and stuff makes the whole effective capacitance way less than the sum of all of them.
Series capacitance reduces the overall capacitance. It's all about current flow. Is this a good design? Well, it depends on what you want. All right, so all this is well and good. Let's see, anything else I wanted to do first?